In this video, we are going to talk about antennas, a little bit of theory, then some simulations. We will design antenna, and then we will do also some practical things. We will measure antennas, different antennas with expensive, and also we will talk about some cheap tools which can help you to actually understand pattern of your antenna and how good the antenna is. Is this what we are going to talk about, Nikola?
Yes, all right, yeah. Today it was a practical session. My name is Nikola. I'm the co-founder of Quarterwave together with my best friend and business partner Bülent. We have founded Quarterwave 1 year ago. We are designing custom-made antennas, and there is a big demand because a lot of people struggling with antennas. And I will show you how can you overcome the struggling with practical things that we use in our daily work. And as you can see here, our daily work is to make antennas also as a handmade prototype here. So sometimes it's faster than to make here a proper design. You go with a copper foil, with a scalpel, cutting the antenna, and then you get very fast results. But you need also to understand the basics of the antenna. And therefore, I switch to the basics in terms of how can you measure, for example, S parameters. So let me go to the antenna basics here. So first of all, if you have an antenna, you need to measure the S11. It's a reflection coefficient. Usually you have such, you have a RF connector, SMA connector, you have a microstrip and an antenna.
I would like to stop you or interrupt you. So
Okay.
what S11 means? Because some people may not be familiar with S
S11
parameters.
is the ratio of the input wave to the reflected wave here. And this ratio shows you how much power is going to the antenna and how much is reflected. And what is also interesting, because a lot of people ask me, why 50 ohms here? Why not 60? Why not 70? And this comes from the past. In the past, the most signals are transferred via coax cable, and you have two extremes. On the one hand, you have power handling, and if you have high power, you need lower impedance. And on the other side, you have attenuation, and therefore it's better to have a higher impedance. And this is a compromise. So in the past, they use 50 ohm as a compromise, and now we are all working with 50 ohms. There's also 75 ohm in TV, but 50 ohm is generally the standard that we are using. And to understand what it means, because in the RF world, we are working with dB, decibel here. And if you have minus 3 dB, S11, this means that 50% of your power is reflected. And it is really bad. Sometimes it could also destroy your transceiver if too much power is reflected. And
so it means I will slow down a little bit. So it means we send some signal to the antenna, it travels to the end of the antenna, and it starts returning back 50% of the power will just travel back to the chip or to the output of the antenna.
Exactly. If you have here 1 watt here of power and you have minus 3 dB, then half watt is reflected back here to the transceiver. And so it's very important to have a good matching here. The antenna need to be matched. But what is if the antenna is not matched? So therefore, in the antenna world, we are using Smith chart. And the Smith chart is a tool where you can match the antenna. So a little explanation. So what you can see is on the x-axis is the real part. On the left side, you have short. On the right side, you have open. And in the middle, you have the 50 ohm. This is the goal that you want to achieve. And if your antenna is not here in the center, if it's maybe here in the inductive zone, so you need components to match the antenna. And if you're inductive, you need capacitors here. For example, you need a capacitor here on the ground and a second one here in series to go to the 50 ohm. And there are also very nice tools. What I use is here the Smith chart tool. Maybe you know this, Robert, or I can also show this tool. It's very cool because you can do this here in that tool here. So if you have the impedance of your antenna, you can here go, maybe here, if you know the impedance here, you know the real part and the imaginary part, or you can go also with the mouse. Put here, for example, here the frequency, where you are working here. For example, here the middle frequency of Wi-Fi. And then you can have here the components that you can choose here. If you want here to match to the center, you use here a capacitor, and then you need a second one here to go to the center here.
Oh, this is nice. Okay, so again, I would like to add a little bit of more information. We need to match 50 ohms because if the output, the trace, and the input are all matched, then it means there will be no reflection, and that's our goal.
Exactly. And the energy and the power is put everything is into the antenna. So this is very important because otherwise only a part of the power is in the antenna. And then I come to the second important antenna parameter, because many people underestimate the radiation efficiency. So if we have matched the antenna, so we have the power here that is going into the antenna, and then you have the radiated power. But the antenna is not perfect. It's a physical object. It's made of metal, of copper, or of steel. Depending on the conductivity, you have ohmic losses here. And this means you have efficiency here. And what does it mean in numbers? So if you have 50% of efficiency, you can maybe achieve 100 meter of range or 12 hours of battery life here if the radiation efficiency is decreasing. So you see that the battery life is decreasing and also the range is decreasing. So it's very important to have a very efficient antenna.
So how do you influence efficiency? By the shape and materials and
yes, by the shape and the material. It's important to know how to design the antennas. There are different designs. Maybe I show you later some examples here. There are different antenna designs for different use cases. So you can't use one antenna design for everything. You need to understand also the environment of the antenna, because the antenna lives from the environment. And always the first question that we ask our customers, do we have a step file from your environment, from your product? Because otherwise you get in trouble, because it's not like a SMD component. It's not like a resistor that you can place everywhere. You need to understand here the electromagnetic behavior.
I would like to highlight here, some time ago I made a video when we were also measuring and fine-tuning impedance of the antenna, and exactly we were talking about this, because if the product displays into enclosure, for example, then suddenly the environment will change, and it's going to influence also kind of impedance and all these kind of things. So it has to be tuned exactly for the environment, as you exactly said.
Exactly. So first, of course, you make your prototype here, but the important part is the real-life test. So you need to integrate the antenna and measure the antenna in the integration space. And in the end, also in the environment where your product is used. So this is very important. So the second important parameter is directivity here. Directivity comes from direction because we are comparing. We are comparing an isotope radiator. This is a theoretical model. This isotope radiator is radiating in every direction with the same power. And this is compared to your antenna. So if we have a directional antenna, you compare this. And to understand it here, I have also here a table. So if you have an antenna which has 0 dBi or directivity with 0 dBi, this means you have a more or less omnidirectional antenna. And if you increase the directivity, so the half power bandwidth, so the beam gets smaller, and also the directivity increase. But the problem is you get increased range, but only for a point-to-point communication. Yeah, if you try to communicate on the back of the antenna, you will get trouble, because you will have no directivity or no power on the back of the antenna, only one direction. And if you combine all these, what we have learned, so you have here the efficiency multiplied with the directivity, you get the gain. And if you take also account here the reflection coefficient here, you get the realized gain. And sometimes people think, oh, I have a high gain, but high gain doesn't mean you have a good antenna. If the antenna efficiency is low, you can have a high gain, but you have a high directivity. And here also are some examples here. So if you have, for example, here 0 dBi antenna with 50% efficiency, so you have minus 3 dBi, so you have a very low range here. But if you get a higher efficiency, you get also more range, and also if you increase the directivity, you get also more range, but you also reduce here your direction.
I understand. So here you can also see like gain when it's 12 dB. It sounds really great, but it is 12 dB only in very specific one direction,
Yes,
correct?
exactly, yeah. Exactly. So this is the theory part. Do you have any questions here?
Not really. We can move to the next one.
Perfect. So we will move to the antenna simulation. And before I go into the simulation tool, we are working with CST. Yeah? And there's also a learning edition, which you can use. But this learning edition is limited, so you can only simulate small models. But for understanding antennas is very good. And I will go directly into the simulation tools. I have also listed here some open tools here. There are also open EMS, which you can use, but you have not the nice GUI that you have in CST. There is also ELMA FEM. This is very strong in multiphysics. And what in ham or hobbyist here antennas are using are also NEC or Feranec 2. It's also very, very cool tool. And there are also options, but in the end, you need more effort here to get to the results. And let me switch here to the tool directly, so we can build our antenna here in the simulation. So you see my screen?
Yes, I can see your screen.
Perfect. So I will explain a bit what we here see. So important is here also here the boundaries here. So what are the materials? What are the units here? We have here millimeter, gigahertz. It's everything okay here. What you can here also make is a background properties here. So we have air. This is also good. So you can also choose another materials. This is all the background material here. And what we have here are the tools for modeling. So what I can do is making here bricks. I can make spheres here if I click here.
So first we set up the environment where we are going to place the antenna. And now we are going to draw the elements of the antenna, yeah?
Exactly. So first of all, you need here to define here the materials. So if we make a quarter wave monopole, so we make a rod here. So you have a radius of 1 millimeter, for example. For Wi-Fi, it's I think here 31 millimeters. So you can here remember 30 gigahertz per centimeters if you divide it to the working frequency, and this is here 2.45 gigahertz is the mid frequency of Wi-Fi. You have 12 centimeters of wavelength, and the quarter of it is 30 millimeters, or 31. And so you see here the rod here. So what I can do is also choose here the material property. So there is a library here of materials. So you can choose here copper. It's lagging a bit here. Oh, I hope it's not here crashing. Oh no.
There is copper here, I see.
Here copper. So I can use copper here, load it here, the preview.
Mm-hmm. And I guess we have to put there some kind of port or something to
Yes,
tell
exactly.
where.
But a monopole need also a ground plane.
Oh, okay.
Yeah. So otherwise it wouldn't work. So we define also a ground plane. Maybe we make lambda half, a bit bigger here. So this is here the ground plane. Okay, now it's shorted. So I will move it a bit above here.
Mm-hmm.
So
So the antenna is above the ground plane, yeah?
yes, exactly. So what I need to do now is to define here the port. So you have here ports here. I will choose a discrete port for that one here. So here is the port.
So this is the point where the signal will.
Yes, this is where I initiate the signal here.
Mm-hmm. It doesn't have to touch the antenna? Doesn't
Yes,
have.
it must touch the antenna. Otherwise, it's in the air and it wouldn't work here. So the port is connected here with the antenna and with the ground plane.
Okay.
And what I need to define in addition is also the frequency. And we can start from 0 to 3 gigahertz here. So now the frequency is defined. And what we have here is the mesh, because the model is cut in cubes. And in every cube, the Maxwell equations are solved, and all Maxwell equations are combined together here to get the behavior of the antenna here. So this is okay. We are under 100,000 mesh cells. This is good. If we are above, this wouldn't work. And now we can start with the simulation here. So this is the accuracy. So if we go lower, the accuracy get better because the power is decreasing even lower, but minus 30 is okay. And when we start the simulation, I think it will be very fast here.
When we are waiting, so I would like to point out, I believe if someone will design the antenna, for example, in their PCB, they can just directly import the models here.
Yes, exactly. But in that version, you have not the possibility to import it. Yeah? You need to do it by hand. But if you use the professional version, of course, you can import the model, and then you can implement your antenna, also the circuit if necessary. But I would recommend to make the model as simple as possible, because otherwise the simulation time is increasing. And keep it simple, because in the end also the simple models are very close to the reality.
So if we would be, for example, importing the antenna which you have in your presentation, we would only need to import the L part and that's it?
Yes, exactly. This would be enough. What I would use is DXF export. So I would make a DXF, and with DXF I can import in Altium, in KiCad, and make a proper design.
And then you have to create also the ground plane, yeah? Correct.
Yes, exactly. I need a clearance here for the ground plane. So let us look.
Oh, it's finished.
It is finished. These are the S parameters here. So we are a bit here too low.
Yeah.
So we need to make the antenna shorter.
I think we need to explain what you say. You say.
Okay. This is here the S parameter, the reflection coefficient, which we are spoken before. And what we see is that the resonance frequency of the antenna is lower than expected. But
we are aiming 2.45, yeah?
Yes, 2.45. And what we need to do is then here to shorten the antenna here, because you have also a finite ground plane. You have also the diameter here of the antenna. So in the theory, you have also the parasitic components. And then you need here to decrease the antenna here. So I have here, so 31 I have. maybe we go here with.
So now we are tuning the shape of the antenna for
Yes.
the target frequency of the Wi-Fi.
Exactly.
We are looking for the minimum on the graph to be at 245.
Exactly. So what I do is here to shorten here the antenna.
And then we will move it. When you short it, we will move it.
Yes, exactly. It will move here to the higher frequency if I short it. If I make it longer, it will go down, which I don't want here. And maybe I also do some field monitors here. So we can also look into the far field. So what I do here is to make some far field monitors here from 2.2, 2.7 here, 0.01. Oops, these two. Here, no, I want here with steps here, exactly. So okay. Now I have also defined here far field monitors. So I restart the simulation, and when it's simulated again.
Far field monitor, it means we will also see the shape?
Yes, we see the far field here. We will also see here the radiation efficiency. It's also very important. But for that antenna, we get a very good radiation efficiency because you have no material with losses. The conductivity of copper is very good. If we use FF4 as a substrate material, of course, we have some more losses here.
But you know what was interesting? I think when we were fine-tuning the antenna, then when you make when you have to adjust, for example, the impedance of the antenna, you will add the capacitor or inductor. You also may move it a little bit again, shift the.
You mean to match the antenna here?
Yeah, when you match it, then you can also shift it again a little bit.
Yes, it's also possible. But if you overdo this here, then you have also losses in that components here. So sometimes it's working if you are very close here to your impedance. If you have one component for matching, it's okay. But if you are on the Smith chart on the border, then it's very difficult to match this antenna. And sometimes you get an antenna which is not very robust, because also the components are very sensitive here. So one change in that components can also change the resonance frequency. So you must be careful with matching. Not always is good to do with matching. And in the end, it's more important that the radiation efficiency is good.
I wanted to point out this. It's not so simple, just make your antenna shorter, because many things will influence the antenna. Okay, it's a little bit more.
It's a little bit more,
yeah.
But
we don't have to go exactly to 245.
No, we don't need here. We see we are under 10 dB. It's very good here. So what we can look is here on the far field here. This is our far field monitor here. Also very great here. So let me show you the structure. So this is the typical donut shape here of that monopole antenna. It's a bit looking above, not complete horizontal, but it's normal because the ground plane it's not infinite here. But this is here a typical here picture of such a monopole antenna. What we can also look, because it's also time consuming to build up these models. I have prepared also models here with FF4. So one antenna design which is very often used is the PIFA antenna, inverted F antenna. It's a very cool antenna because the antenna is matched with the stub to the ground here. It's like an inductor. It's a matching element in the end here, which you are doing with that trace. So here is the inverted F antenna here. So in the end, it's a monopole here. So
Mm-hmm.
a monopole here with a 90-degree here, it's here to the ground. And then you have here the trace here, which is inductance here to ground. And I have already simulated this model, so we don't need to wait here for results.
Oh, this
And
looks
see,
different.
very good
Yeah.
here. It's perfect match. And if we look here on the far field here, so let me go to the 3D. Yeah, something like that here. Also not bad here. It's a bit here, yeah, what is it called here? Not looking a bit here above, but if I look here this way,
It's nice.
it's more or less omnidirectional.
Mm-hmm.
And also the efficiency. So this is the radiation efficiency here. We are around here 70, 75, but this is normal here for such antennas here, because we have also here the FR4 material. The FR4 material has also electrical losses here, tangents delta, and that's normal here. And this is how you can here try here tune the antennas here, where you have also possibilities to make here a parameter sweep. So you can also define here parameters and let them sweep if you want to find the sweet spot of the antenna and not to do try and error as we did here now here to shorten the antenna. You can make it automatically. There are also a lot of optimization tools which you can use here.
So it will kind of find the optimal length, for example.
Exactly. It will. So there is a goal that you can define, and then the optimizer will find the best length here of the antenna.
And the shape of antenna, I think there are many different kind of shapes. So maybe if someone is designing antenna first, they need to know where or what kind of shape of the fields maybe they need, what kind of size they have available, and then they can go through all the kind of different shapes, and then maybe
that's just right. So you know to need you must know the environment here, where you want to integrate the antenna, where you want to place the antenna here. So you must understand the electromagnetic behavior, and therefore you can also here simulate the surface currents here. So this is also very cool here to see how the surface currents are propagating over. You can also animate this here. Let's see. These are with arrows here. So you can see also here the current flow here. We set here.
Oh, now we can see we need the ground plane.
Yeah, you need the ground plane because the ground plane is a part here of the antenna. Without ground plane, this antenna wouldn't work. So the efficiency will decrease here if you make the ground plane shorter. Yeah. And what you can also do, but it's not here in that learning edition, you can also calculate here the eigenmode here. So there are different solvers here, and there's also eigenmode solver, which means you can find out what the mode of the PCB is. And if you know how the electromagnetic wave is propagating over the PCB, you need to find the spot where you can excite the PCB. Then the PCB itself will be an antenna. So this technique is called characteristic mode analysis. And if you know the characteristic modes, you need only to excite them. It is not so easy as I tell you, but this is the way how you can make everything to antenna. So if you have a PCB, you can make a PCB to antenna.
I made a video with Katerina, I think, where we talk about influence of the whole board, because this what we have here, it looks more like ESP32 module or something like that, different shape of the antenna. But sometimes this kind of module can be placed on bigger PCB, which also has ground plane, for example, and then this is going to influence the antenna environment again. So yeah, that's why I think it's very important, or it's nice to have this kind of simulations. Then we can understand a little bit more the behavior of the whole system, not only
Yes,
this small piece.
exactly. Because the goal is to understand the electromagnetic behavior. First of all, we want here the antenna is only emitting in that mode what we want, and the other side is the unwanted emissions. So we can also suppress the unwanted emissions. If we think on antenna radiation, we must also think on EMC and EMI, and we can also reduce with that techniques also the unwanted emissions. So it's also very important also if you think on signal integrity. So in signal integrity, you are controlling the current flow. You are looking that the return current flow is not so high, because otherwise you get also trouble here. And this is similar here.
So now we simulated our antenna. What is the next step? We are going to build it.
Exactly. So the next step here, we are going to build it. I show you in the initial slide here. We go back here, which tools you need here to build your antenna. So what you need is here a copper foil here. So if you want to make very fast prototypes, so you need a copper foil, but one advice, use a copper foil with conductive adhesive here. Otherwise, if the adhesive is not conductive, you get a capacitance and the antenna is not working as you want. And then you need a scalpel, maybe if you want to make a rod antenna, copper wire, FF4 material, and some pigtails here with semi-rigid cables. And then you can make such like here prototypes, like I made here. I have this, I have here, this one here. We will measure here later here. And the second step would be, if you have proven that that antenna concept is working, you can also make your own PCB. Or if it's too big here, I have also something like these antennas here. This is a Vivaldi antenna. It's a broadband antenna, which I use here for measurement here. And for that, for that antennas, I export the DXF to KiCad, to Altium, then make the production data, and then here build the antennas, for example, at JSC-PCB or another manufacturer, and then I get here the prototypes and measure the prototypes.
Why it is the shape of this? I'm just curious.
This shape of antenna, it's needed if you want to make a broadband antenna here. This because this covers a broad frequency range from 500 megahertz to 600 megahertz, and the wave is here
6,000
here. 6,000, 6 gigahertz. Yeah, exactly 6,000 here, and therefore you need this shape, because you can imagine that are like here, like the logarithmic antennas, like the log pair antennas. You have a lot of here waves here, and you can cover a lot of here frequency range.
So it needs to have all the kind of, it has to include all the kind of lengths of the waves.
Exactly.
Okay, so now we build the antenna, and I think now this is the most like kind of something what not many people do, how to measure it, because usually
how to measure it, yeah. And the first step here is here to measure the S parameter here.
Before you continue, I would like to say my way to measure antennas was usually like I switch it on, I go to next room, and it's working. So
it's working.
But that's not how we should measure the antenna, correct?
No. You can do it if you use antenna design, but it's better to start with the S parameter to measure the reflection.
So tune the antenna, yeah, first.
Yes, and then tune the antenna. You can tune the antenna with a structure or with matching networks. So there are different here devices which you can use. There are, of course, very expensive devices like from Rode and Schwarz here, which are very good. They are really good, but sometimes you don't need such expensive devices if you want only measure some reflection coefficient here. And there are very cheap here measurements devices like the Nano VNA here. It's very affordable, 100 euro, 200 euro here. And you can measure here S parameters. I think there are versions to 3 gigahertz. So you can, I think, 160 euro at Amazon. I have looked last time here. And that's enough here for
So
only
standard Bluetooth Wi-Fi antenna you can measure with this or tune with
yes,
this. So I would
yes.
like to point out, basically, we can see on the display, these are exactly the charts what you showed at the beginning when we have to move by adding capacitor or inductor, move
Yes.
the impedance of the antenna to 50 ohms. Yeah.
Exactly. And what I use personally, I can also show you is
But
here the
okay, let's go back. So
ah,
you need to
go back
connect.
here.
You need to connect this to the input of the antenna, correct?
Yes, and I need to put here this here on the antenna here. I have here you can see it here on the video here. So here I have here my here network analyzer. So what I need to do is here to put my antenna here on that port and to measure here the reflection coefficient. But before I do this, I need to calibrate here my network analyzer because I don't want to measure the cable. I want only measure here the antenna itself, and therefore I need to calibrate here my network analyzer. And I can show you. I have me move here to that here.
So this is the one what you have.
Yes, this is the one what I have. I use here the Sigland here because I can not only measure here the S parameter, I can also measure here spectrum. I can also make here some here modulation analysis. It's a very cool tool because one tool for a lot of measurement activities here, which I do. And for the S parameters here, first of all, I need here to define here which measurement frequency. So I want to measure Wi-Fi here. So I go here from start here from 2 gigahertz to 3 gigahertz. Then I can here define the number of points. Maybe we can do here 1000 points here. So when we have defined the frequency, and then I need to calibrate here.
So I guess now you need to leave it open and then close or something like this.
Yes. So with the one port calibration, I need to calibrate here with various three standards. I have here one open here. It goes very fast here. Can do it here. So first of all, I put here the open.
So you connected the cable which you will be connecting to your antenna.
Yes. I have here the measurement cable, and the measurement cable I don't want to measure this cable, so I need to correct it here. And then I start with the open, press here the button, and then go with the next here.
Open, it means there is nothing connected to the cable.
There's nothing connected here. Yeah, more or less, but this is defined open here.
Okay.
Otherwise here, this will not work properly. So the next one is the short. Maybe you imagine the Smith chart here. Short here on the left side, the open on the right side here. So when I press enter, and last but not least here, the 50 ohm, the match one. So I enter this here. Then I go here to see in the Smith chart if it's properly calibrated. So I can go here.
So you now will see the 50 ohm exactly. Yeah.
Exactly. So you see here the point. So you see it's properly calibrated. But what I need to do in addition, you see here the antenna that I want to measure. This is the inverted F antenna. And there is the pigtail, and I don't want to have a pigtail in my measurement. Therefore, I have here one with open. You see, we have this electrical length, this additional. And this I want also to be calibrated. And I go here to...
So this is basic. Now you connected the cable which you have
Yes.
in your antenna.
Exactly. And I go here to the port extension here, and I go to calibrate this. So this is also not in my measurements anymore. So I measure directly on the antenna port. So now I put the antenna on that port here.
It's going to be perfect 50 ohms.
Yeah, not bad here, not bad. So let us set a marker. Frequency. Let me look here.
So now it is showing all the frequencies from 2 to 3.
It's
the
all
position,
the frequencies. Maybe it's, if we look here on that here one here, it's better. Go here with the marker here. So maybe a bit too low. If I cut it a bit here, it would go higher, but it's very good here. So we are under 10 dB, so it's a very good antenna. And you can also see, show here in the picture, if I go with the hand here, to see that it is sensitive here. So the antenna is radiating here.
Can you show where is the 2.45 in the Smith's chart?
Okay, we go back here to the, where is it here, measure? Smith. Oh, it's not so far away here. So I would say it's good enough here. To match this antenna doesn't make much sense. So what I would use is only to make it a bit shorter, so because it's too long. And I always make my antennas a bit longer, because then I can cut it to the frequency. Otherwise, if the antenna is too short, it's not so good. So you see a very good antenna. I have also other antennas here. So this is the inverted F antenna. I also make here this antenna here. Is also not bad here. This shape here. But this is not so good here. Also not so bad here. You look here.
So 50 ohms, where should be the 50 ohms?
50 ohms here. Yeah, it has 10 dB, but if I look in the Smith chart,
there
here's a 50 ohm, and you need two matching elements here. But it's okay. It's okay here, because it's handmade here. So
you have one more antenna.
I have a lot of antennas here. So I have also here this monopole antenna here, the rod antenna with the radii. Okay, this is not good because
there is no cable.
The port extension here.
Yes.
So it's not properly.
Yeah.
But the antenna, it's a bit lower from the impedance. Usually I would do the radius in a how is it called here, to bend it here down here. If I bend the radius down, the impedance go higher. I think here 40 ohm or a bit lower. If I bend here the radius, impedance get here higher, and I go near to 50 ohm. But this is also here. So this is my reference antenna which I use here. So we will see it here in the measurement here, because this is the S parameter measurement here, but this is only the half of the story.
Yes.
So we want to also see the radiation pattern here.
Yes, that was, I'm curious about it now. So this is basically, we measured the kind of this is only part of the measurement, the first one.
Exactly.
Now we would like to see the fields.
Yes, and the field is very interesting here.
But we can go back to our presentation, because you started talking about the device what you are using. Yes, and I interrupted you.
Yeah, no problem here. There are different devices, so sometimes also such devices like the nano VNA are enough here for measurements. Doesn't need to be always the best one. And what I told you, I use this one here because I can measure S parameters, spectrum, also modulation, and this is very cool because it's also affordable, $2,000 or $3,000, and you have here 3 devices in one. So it's very, very nice here. And as I told you, we need also to measure the antenna pattern here. And this will be also very interesting because there are also different measurements. You can do it in free space, you can use an anechoic chamber, but what we are using here is self-made here with ESP32. How is it? How is the setup here? So
I would like to highlight ESP32, okay?
Yeah.
We are going to measure the field around the antenna with
Yes.
ESP32.
With ESP32. So what you see is I have here a device here where is ESP32, and I have a firmware which makes the one to a transmitter and the other one is a receiver. Yeah, and it's something like this is the access point, and the other one is the client here. And what I do is measure the error SSI, and then I have a rotation table, and the rotation table is rotating, and I measure for every 3-degree RSSI, and this is plotted to antenna pattern plot, and then we can see the antenna pattern here. Maybe I can show you also how is it inside here. So it's not much inside here. It's only the ESP32 here, a battery. The cool one is that this version of the ESP32 has also a battery charger, so I can charge it with USB-C. And I have one firmware, so the devices are equal. So I can, if I put it here on, so you see it's green, and green means it's in transmit mode. So, and if I hold longer, it's red and it's in receiving mode.
So now explain a little bit more. So it means, for example, you are using the standard Bluetooth Wi-Fi output, and you are sending in one mode, you are sending out the signal,
Yes.
And in the other mode, you can read how strong the signal is.
Exactly. I measure the SSI. And on one channel here, so it's in the moment it's a fixed channel, but here to see how the antenna is working, it's enough here. And maybe we go directly into the measurement here. So if I close this here, I have already opened it. So what I need to do is here to start here my rotation table. I have here some software here to start it here. So now it's rotating here. And what I do, I place this here on the rotation table. Maybe I can also
you can show it
shortly here the camera here. You can see it here. So it's rotating. On the other side, it's the receiving antenna. So here is my receiver, and then I can start with the measurements here. So now,
and the antenna what you are measuring is connected to the transmitter, yeah, correct?
Yes, it's to the transmitter, and I am starting here with the reference antenna here. So let us go here with the reference here. Everything is working, and you see it's receiving here. So it takes 1 minute because if the velocity of the rotation table is in 1 minute here. It takes a bit of time. If you have any question.
No, I don't know. It's I think it's really cool because I think it's very important to get this kind of sense. If someone designed their own antenna, they really should get some kind of results to get the sense of where are the fields and how strong they are actually.
Yes, and you can do it with things that cost nothing, more or less. Yeah, ESP32. The other things are also in some euro. So now we have finished here with that
perfect circle.
reference antenna.
This is perfect circle.
Perfect circle, yeah.
Yeah. Can you put there different antenna?
Yeah, I put a different one. Yeah, I will put here the directional antenna.
The one like
here, this
butterfly? Yeah, okay.
This one, yeah. It's very cool.
But with this measurement, you are getting only some kind of relative numbers, so you don't really know how strong
No,
it is?
it's okay. Relative is okay. So if I know how the gain of my reference antenna is, the relative is enough here. Because in the development, you need only indications here. So if the antenna is bad or not bad, and in which way I need to optimize my antenna. So now I would. Oh,
This is so cool. I like it a lot.
So DOT. So oh, it's much more here. You see. So this is here the antenna which has a high directivity.
Okay, and I guess now we are going behind the antenna.
Yes, yes. Now it's behind the antenna here. And if you would like to see the shape on the top or something, then you have to rotate it. Yes, exactly. So what I would do usually is here to measure in X, Y, and Z, or to rotate the antenna and measure that on that cuts here.
This is so cool. Can you use also different devices, like maybe like software-defined radio?
It's also possible, but it's more complicated. So of course you can use software-defined radio with GNU radio, which is very popular here in the Linux world here, and you can do everything here. In the past, it was really difficult to do this stuff, but nowadays with software-defined radio, you can cover 6 gigahertz. So the most software-defined radios go until 6 gigahertz, and you can measure it with no problem here.
But this is very simple because basically you have very simple firmware which just reads how strong the Wi-Fi signal is. Yeah.
Exactly. And I'm only comparing it here. So you can also here. You can measure this one here.
Yeah. Okay, put it there. I'm curious.
Here, the previous antenna here. So.
Can you compare this? If you would like to get some kind of maybe better results, shall you buy like kind of certified antenna and then compare these your measurements with?
Yeah, you can buy a certified antenna, or you can measure the antenna in a certified laboratory. You get a report of the antenna, and then you have your reference. This would be also possible. Yeah. So now second.
And what about the table? You made the table by yourself, or you bought something on internet, or?
No, by myself here. So these are standard components here. You have a rotation here, motor, and the other things you get into Baumarkt here, called in Germany here. It's simple stuff here. So this is the previous antenna, the green one. It's not so good like the other one here. Because it's too short here. If it would be a bit longer, we would have here also more directivity. But I have no other cans. I have used what I have. So what you can see, you can make everything to an antenna if you know how the physics is working here.
So when you created this setup, you started connecting everything what you had, yeah? Spoons.
Yes. I have looked. What can I make? Or what stuff I have here around me, and what can I make to an antenna here?
Okay, so Actually, what do you do? What your company does?
What
Tell me a
my
little bit more.
company does, let me
Yeah.
go to the slide here, when I can explain it here.
How did you come up with these ideas, and why did you build it?
Yeah. Yeah, why we do build this is to show the people that RF and antennas, it's not black magic. So
Mm-hmm.
it's about understanding here physics. And as I told you, first of all, you need to understand your environment here and also the electromagnetic behavior of that environment. And if you understand this, you can make also a proper antenna. It's similar like signal integrity. That's also a part what we cover. So we're also doing signal integrity simulations, power integrity simulations, and to close the loop, we are also do pre-compliance measurements. And I recommend everybody to do pre-compliance EMC, EMI measurements. Otherwise, you get big trouble in the test laboratory. I have made many bad experiences, so it's good to do it here from the beginning, and also the antenna design to do it in the beginning here.
Mm-hmm.
Otherwise, you have no chance. In the end of the development process, you have no chance because you have no room here for the antenna. And you have a timeline here. You need to be finished with your product. So, and what you need is not expensive measurement equipment.
Mm-hmm.
Sometimes you need only TEM cell or GTEM cell. We're also producing our own measurement equipment. So, because if you know how RF is working, you can also do your own measurement equipment. Sometimes we need to do it because in the last companies, not every company wants to spend here in measurement equipment. So you need to be creative and to do your own measurement equipment. And what we are doing is to do here integrated antenna solutions. So first of all, we try to we use here integrated antenna like we do it here in that project here on the left one. This is done here for our partner and customer Enrich. This is a sensor which is working with NeoMesh. And NeoMesh is used in the lower frequency band, 868 megahertz. And this is very interesting because we are using also here the battery as antenna. So if you know how to excite here the right modes, the characteristic mode, you can also use components that you have in the PCB, which you normally decrease the antenna performance, increase the antenna performance,
Mm-hmm.
because the ground plane is enlarged with that here battery. But on the other hand, this antenna design you can't use here for the variable, for example. If I would use here that antenna design here for the variable, which is stick to the body, I get a problem because the most of the electromagnetic wave is absorbed by the
Mm-hmm.
body. So you need to go into the second, in the third dimensions here. So you can do it, for example, with 3D antennas. So 3D bending here antennas here, which we use here. And then you have a second problem because you are narrow band. And if you want to overcome the narrow band, you need to switch the antenna. So you have two matching networks and you can switch that. Yeah. So what we can see here on the screen is here the lower LTE band here, band 20 and band 8. And to cover this band, you can't do it here with a one matching component. You need two matching networks and you can switch between.
Mm-hmm.
And there are also devices which are also even more constrained, like ultra compact tracker. We are also developing chip antennas, and you can see here on the picture. So you need four matching networks to cover the whole bandwidth here. So the complexity increase, but you see there is always a possibility to overcome this physical constraints.
Mm-hmm. So you can design antenna for all these, yeah, cover all
Yes,
these.
yeah, for all this and also other areas. So Bülent and me are also worked a long time in automotive. So we know also all kind of automotive antennas and also know a lot about radar antennas. So every antenna that you can imagine, we have maybe here designed. And to show you also some interesting products. So we are also working on products and also looking on new technologies. You know here NTN. NTN is the non-terrestrial network. So it's a satellite communication. but it's bidirectional. It's not like GNSS. GNSS is broadcasting, and this communication technique is bidirectional, and you need good antennas. So because you can imagine here, the satellites in GEO and LEO orbit are very far away. The link budget is poor, so you need a high gain, and you need also a circular polarized antenna. The most antennas that you find are linear polarized, and you need circular polarization. Otherwise, you lose also additional 3 dB. And this antenna covers both frequencies, the L and the S band, and also circular polarized. And another interesting radio or technique is ultra wideband. Maybe you know also this ultra wideband stuff. So ultra wideband covers very broadband frequency. I think it's starting from 3 gigahertz to 10 gigahertz, but only a few bands are interesting. The band 9 and 10 is very interesting because you can use it worldwide. The other bands are more critical here. So what we are also developing is antenna modules because it's very complicated here to make RF, and not all companies have the knowledge and the measurement equipment and tools to develop such antennas.
So they can just buy your modules.
Exactly, and we have a standard interface here, a pin header, and on the pin header you have a SPI connection, and you can control here that antenna. I think I have also here one sample here. Here, this is here the eval board which I use here, and this antenna is very small. The antenna module is 29 by 10.
Yeah, I can see it on the top of the PCB.
You can see here.
I can see it. Yeah. When you show it, it was on the top of the PCB. Yeah.
And on the top here, exactly.
Yeah.
No. It covers one hemisphere. It's a directional antenna that are 2 patch antennas, because we are speaking about AOA, angel of arrival. For angel of arrival, you need 2 antennas, and we are using 2 patch antennas. And this helps the customer to test things very fast, because usually you have big eval boards here with big antennas here, and these are not very comfortable for doing measurements, real measurements, and therefore we have developed our own module, and we are also developing our own measurement equipment, like that one with the ESP32, or like here the pre-OTA box. OTA is over the air measurements, for example TRP measurements here, transmitted radiated power. So the idea is to put your device under test into the box, to press a button and to get indication.
Oh, nice.
Yeah, but it's very complicated to get the shielding very properly. The electromagnetic wave finds everything a way out here. So the manufacturing is also very important. If you make such like things here, like that boxes, you need to think about how you shield it here.
Nice. So if someone would like to contact you, can you show your website?
I can show you my website here. Contact.
So you will be making kind of like affordable product to measure shape of the field around the antenna. Oh,
exactly.
Cool.
This is here our product here. We have a lot of articles here. Also, if you are interested in antenna basics here, you can go here and read our articles here. So here, like here matching here, why matching matters here, or here the prism effect here with the switching techniques here. Very interesting articles. Also here with some interesting pictures to remember. What does it mean here? For example, ground mirror. You can imagine here, like in a mirror, you see only a part of your face here. And this is like the ground. If the ground is decreasing, also the antenna performance is decreasing. So these are very nice articles here. So about antenna basics, but we have also case studies here. So something here like here smart farming here, or smart antenna solutions. So we are also always looking what are the challenges, what are the real world problems, and how can you overcome the real world problems with good antennas here.
And I think you will be also on embedded world.
Exactly. I can show you here. We are not only on the embedded world, also on the Mobile World Congress here. So we have here a booth. So here is we have a partnership here with Endrich, and we are on the Endrich booth on the Embedded World here, Hall 2. And 1 week before, we are on the Mobile World Congress here. So also here together here with here the Congress here square, where here's the stand. And it's also very interesting here to get in contact with the people there, because Mobile World Congress, it's our world, and also Embedded World here. This is very interesting, and I am very happy to be there and also to meet you there, Robert.
I will go. I will go.
Yeah.
Yeah, we met also last year. So
Yeah, we made it also last year. You are also on the Mobile World Congress or only Embedded
no,
World?
just Embedded World.
Just Embedded
Because
World,
2 weeks before there is DesignCon conference in the US. So I just go to DesignCon,
okay.
then I return, and then I go to Embedded World.
Okay.
Yeah. Okay. So I think that's everything for today. If someone would like to meet you, and it is still before these exhibitions, they can go to your booth and talk to you. And if they have any questions, if people have any questions, maybe what kind of other video we could make and talk about, they can leave them in comments. So thank you very much, Nikola, for this. I really hope many people will find this useful, because it was very quick introduction into antenna design, but we covered a lot to give some kind of generic idea how to go, what are the steps, and now I think people can go by themselves and maybe search for these specific steps.
And if they have questions, they can ask us here. And thank you here for the invitation here, Robert, here, and to show here the topic, because we are doing it with passion here. So we like what we do here. And if you do what you like, you don't need to work. You know.
Thank you very much, Nikola.
Thank you, Robert.
That's all for this video. I hope it was helpful. If you would like to learn more about electronics and board design, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KeyCut, and also courses covering many different topics, for example, FPGA, EMC measurements, and so on. Visit our website at fedevel.com. That's all for this video. Thank you very much for watching, and don't forget to leave your comments. See you in the next video. Bye.